So we would like to invite the first speaker, Nandeeka, to present her TeAAL, a declarative framework for modeling sparse tensor accelerators. Over to you, Nandeeka.
Hi. Can I start?
Yeah.
Okay. I'm Nandeeka Nayak, and today I'm going to be talking about my work TeAAL, a declarative framework for modeling sparse tensor accelerators. This work was done in collaboration with Talua Odemuyoa, who you heard from earlier, Shubha Mugari, my advisor, Chris Fletcher, Michael Palauer, and Joel Emmer. I'm sure that people at this conference don't need a refresher on what a tensor is, but one piece of notation to clarify here is that in this presentation, we're going to use the word rank to mean the mode or dimension of the tensor. So for example, we say that a matrix has two ranks, rows and columns. As we've seen, sparse tensors appear in a variety of applications, and this presentation will focus on hardware acceleration for these workloads. We want to note here that unlike many of the other presentations, the kernels that are designed for hardware accelerators are often even more strange looking and even more customized than anything that you would see in software, since even the hardware can be fully customized. Unfortunately, because the sparsity in real-world tensors can be highly irregular, leading to inefficiencies caused by unpredictable data reuse patterns, additional metadata overhead, low arithmetic intensity, and so on, accelerators have been designed to have a whole host of custom optimizations. This means that accelerators that supposedly solve the same problem, like these four sparse matrix multiplication accelerators, often appear quite different. Because there's no separation of concerns between the different features that comprise designs, each one seems like a one-off exotic technique. Without this separation of concerns, it's difficult to perform apples-to-apples comparisons between existing designs or evaluate the impact of proposed design changes. This results in the following accelerator design methodology we see today. First, one must describe an algorithm. Prior state-of-the-art uses block diagrams, natural language, pseudocode, and sometimes equations to do so. The specific sparse tensor formats are usually entangled within these descriptions. They also use tools to model the architecture, including its microarchitectural components and memory hierarchy. However, these descriptions usually cannot be understood by a computer. So to evaluate the accelerator, an architect usually writes a custom simulator. Because writing these simulators is so time-consuming and error-prone, it's generally not possible to do so for all prior works. Instead, architects try to scale the results reported in prior work to their own hardware parameters. Finally, unfortunately, to extend designs, without a separation of concerns, architects must go back to step one and describe a totally new algorithm. TeAAL enforces a separation of concerns by defining a hierarchy of declarative specifications for describing accelerators, following the paradigm of works like Halide and Taco, which we also heard from earlier. These specifications describe the algorithm in two parts. A set of equations we call a cascade of einsums, and a mapping describing the scheduling of the computations within the cascade. Separate specifications also describe the architecture and sparse tensor formats. A binding specification ties everything together. Not only is this specification concise enough to be human readable, it's also precise enough that from it, TeAAL can automatically generate a simulator. Comparing accelerators requires writing the specifications for each of the accelerators you wish to compare and running the simulator. Separation of concerns means that it is easy to normalize hardware parameters like memory bandwidth and buffer space. Finally, one can extend a design by incrementally modifying the relevant specifications. More concretely, our work makes several contributions over the state of the art. Oh no. First, as noted earlier, we recognize that the specification of an accelerator can be decomposed into a hierarchy of specifications that separately contain details of the algorithm, data flow, architecture, and sparse tensor formats. We show that seemingly monolithic kernels, like sparse matrix multiplication, in practice are often better described with a sequence or a cascade of einsums. We also describe a set of content-preserving transformations on tensors that modern accelerators apply to sparse tensors to improve the performance of the cascades they compute on. With TeAAL, we provide a simulator generator that translates accelerator specifications into validated performance models. We show that these performance models can reproduce the characteristics of 4 state-of-the-art sparse tensor algebra accelerators with high fidelity, and demonstrate the potential of TeAAL as a tool for design space exploration by using it to improve an accelerator for vertex-centric programming for graph algorithms. We achieve improvements on both best first search and single source shortest path over the state-of-the-art. All of this is enabled by the observation that while each accelerator may appear quite different, the macro architectural templates for most accelerators are the same. Accelerators are organized as a hierarchy, with buffers and compute units local to each level. The differences between accelerators come from the number of levels, what components are included, and how the data is orchestrated. Therefore, we classify the accelerator microarchitecture as a low-level detail and focus on the algorithm and data flow the accelerator implements. As a running example for how TeAAL represents sparse tensor algebra accelerators, throughout the rest of the presentation, we will consider the outer space accelerator. Like the other designs shown earlier, to perform sparse matrix multiplication efficiently in the presence of irregular sparsity, outer space proposes a set of custom strategies. At a high level, outer space uses the multiply merge algorithm. If we call the matrices to be multiplied A and B, then outer space first multiplies columns of A with rows of B. These multiplications produce partial products, which are stored in a compressed array of linked list representation. Outer space reduces these partial products together by first sorting them, and then adding together the elements that will contribute to the final, to the same element in the final output. This was all very complicated. Let's try to break it down using the abstractions TeAAL proposes for simplifying the design of an accelerator. First, let's quickly review our definition of an einsum. Just like Tulua described earlier, our operational definition of an einsum looks at representing kernels in the tensor index or extended Einstein summation notation, which we will shorten to einsums. We represent matrix multiplication as follows. Matrix A with ranks M and K multiplies with matrix B with ranks K and N to produce matrix Z with ranks M and N. The einsum provides an exact specification of what computation is performed. For each valid combination of K, M, and N coordinates, the kernel must perform a single multiplication. When multiple products are meant to update the same output value, they must be reduced together, in this case with the sum. We infer which ranks the einsum reduces across by identifying ranks that appear on the right of the equal sign, but not the left, like K in this example. Additionally, the order the ranks appear in the einsum has no meaning in our notation. Because the rank order is an implementation decision given in a lower level specification, we prefer to write the ranks in alphabetical order. We will instead write matrix multiplication with A as AKM instead of AMK. However, the outer space data flow we discussed earlier looks a bit different from this single einsum. Rather than doing the whole kernel in one shot, it breaks the kernel into 2 distinct phases. A multiply phase that takes the input matrices A and B and produces an array of linked lists of partial products, and a merge phase that consumes this data structure to produce the final output Z. TeAAL therefore introduces a new abstraction, a directed acyclic graph or cascade of einsums to represent kernels performed by an accelerator. While outer space does perform matrix multiplication, outer space's data flow is better represented by 2 einsums executed sequentially. First, the accelerator multiplies A and B together to produce a 3-tensor T, representing the array of linked lists of partial products we saw on the previous slides. Notice that in the first einsum, all of the ranks on the right of the equal sign also appear on the left, so there is no reduction. Then T is reduced across rank K to produce the final output Z. Cascades of einsums are found in a wide variety of kernels. The gamma accelerator for sparse matrix multiplication uses a slightly different cascade to separate the axis of B from the rest of the computation. The Toeplitz expansion, or M to call for convolution, can be represented with 2 einsums. One that accesses elements of the input and one that performs the computation as a matrix multiplication. Some implementations of MTKRP factor the kernel into 2 einsums to reduce the number of multiplications required. We also found that cascades of einsums are general enough to describe the Cooley-Tukey fast Fourier transform. The takeaway here is that cascades of einsums are a general abstraction, expressive enough to describe kernels in many domains, from tensor algebra to machine learning to signal processing. Cascades of einsums allow us to separate the specification of outer space into two distinct phases. However, in addition to reduction, during the merge phase, outer space performs a sort of the intermediate tensor. This sort was not evident from the two einsums presented a few slides ago, which brings us to our second set of abstractions, content-preserving transformations on tensors. Let us first understand why this sort is required. To exploit spatial locality, outer space would like to read its partial products in the order they are laid out in memory. We call this a concordant traversal order. Outer space forms the T data structure by placing in a given linked list all partial products that will correspond to the same row in the output, or in other words, have the same M coordinate. Let's take the first set of partial products corresponding to all partial products where the M coordinate is 0, as on the slide. We first read an element of T, which updates Z01, then the second element of T, which updates Z03, and then the third element of T, which updates Z01 again. Unfortunately, if we use a concordant traversal on the partial product, updating the appropriate locations in the output as we encounter them, then we have a very random or discordant access pattern on that output. A careful listener might be asking, why do we need the sort in the first place? We could have just built the partial products in a different order. Unfortunately, the need for the sort is a direct result of the data flow used during the multiply stage. Without changing that, we would need to sort the partial products before writing them to memory instead. So to mitigate this discordant traversal problem, outer space first reads a row of partial products concordantly and sorts them by their end coordinate. Once the partial products are sorted, it can achieve a concordant traversal on the output during the merge einsum. We see that this new traversal order first finishes updating Z01 before moving on to Z03. We call this transformation content preserving because it not only changes details of how the tensor is represented, but doesn't change anything about the values stored in the tensor itself. TeAAL supports a few other such transformations that together help improve spatial locality, load balance, and buffer utilization. Accelerators are described in TeAAL with a set of declarative YAML specifications. Here is the TeAAL specification for the einsum and mapping of outer space. As we can see, the specification includes the cascade of einsums as we described it earlier. To validate the performance model, we also described with TeAAL 3 other sparse matrix multiplication accelerators whose block diagrams I showed at the beginning of the presentation: gamma, extensor, and sigma. While from the papers that proposed them, these accelerators each appear quite different, we were able to describe them all using the same language. On the slide, we show the einsums and mappings for each one. The takeaway here is that TeAAL captures the salient characteristics of each accelerator in about 30 lines of code. From these specifications, we generated performance models, which we validated using statistics in previously published results or private communication with the original authors. The graph on the slide compares the previously reported memory traffic numbers R on the left with TeAAL's memory traffic model T on the right for outer space on 5 sparse matrices, broken down by tensor. As before, A and B are the inputs, T is the intermediate, and Z is the output. Because we're validating our model, we would like our predicted memory traffic to be as close as possible to the reported values. We also validated TeAAL's memory traffic model on extensor and gamma. TeAAL accurately captures the memory traffic performed by these accelerators, incurring an average error of 3.8% across all accelerators on all benchmarks. We also used TeAAL to model the performance of each of the 4 accelerators. TeAAL achieves a very low modeling error on extensor, gamma, and sigma. Again, because we're performing validation, we would like the blue reported bars to be as close as possible to the TeAAL orange bars. We overestimate outer space's performance, but we do so by a consistent amount, around 80%. As we saw in the previous slide, our average error for outer space's memory traffic was 1.8%. We therefore suspect that this discrepancy comes from an undocumented and therefore unmodeled feature of outer space's PE microarchitecture. We also validated TeAAL's energy model, and the details of this are available in the paper. To demonstrate TeAAL's generality, we modeled accelerators in a domain outside of tensor algebra. Vertex-centric programming is a unified paradigm for representing graph algorithms like breadth-first search, single-source shortest path, and PageRank. We use TeAAL to describe existing accelerators for this domain and propose our own optimization. So, Graphicionado is an accelerator for algorithms written in this paradigm. We see that the cascade of Einstein's abstraction extends naturally to kernels beyond matrix multiplication to represent the accelerator. The accelerator GraphDynS models this cascade to reduce the memory traffic required. We further improved GraphDynS's cascade by optimizing the mapping. Looking at the results, the first bar in each group is Graphicionado, the middle bar is GraphDynS, and the bar on the right incorporates our mapping changes. Our optimization achieves improvement over GraphDynS on both breadth-first search and single-source shortest path. This presentation described the core insights behind TeAAL, that modern sparse tensor algebra accelerator features can be represented as cascades of mapped einsums and constant-preserving transformations in the constituent tensors in said einsums. We use this insight to design a specification language for sparse tensor algebra accelerators and build a compiler that translate these specifications into performance models. We validated the performance models and used TeAAL to improve accelerators for vertex-centric programming. The entirety of our paper, which describes a few additional insights, the details of the other specifications, how those specifications can be used to generate a performance model, and so on, is currently available in arXiv and will appear in Micro this year. Thank you.
Great presentation. Thank you. Is cascade intuitively a DAG, or are there some fundamental abstraction differences between what a cascade is?
Yeah, so the cascade is just the word that we use for a DAG of einsums, where the nodes are tensors and the edges are the uses of them. Or the other way around, where the nodes are einsums and the edges are tensors. Yeah, so we do support like a single link interconnect, right? Where there's a single bandwidth that is being communicated, but currently the performance model doesn't support other kinds of interconnects. However, we view this as like a implementation detail of something that we haven't implemented yet, as opposed to a fundamental limitation of our approach.
What order should I do? Put it in presentation mode first or share screen first? Great. I'd like to thank the organizers for creating this workshop. Hope this will be an annual event. That's the plan. So this talk is about a project that is a collaboration between me, interest in high performance computing and optimization, and Vivek Srikumar, who is my colleague, who is in NLP. And so we were trying to think in terms of how can we create a project that combines some aspects of optimization and machine learning. And so this work is that of his PhD student Ashim Gupta. So he's a very prolific publisher in NLP. So this is something on the side that he's doing, and then my PhD student Sina. So essentially, this is about trying to see if factorization, how can factorization be effective in the height of LLMs. There's actually a lot of work in this domain, and in general, we found it quite difficult to compare approach A versus approach B because there are all kinds of differences in the schemes that you implement. And so we said, let's just start from scratch and then try to compare, start with, the goal here, I think this has been mentioned in previous talks to you, the sizes, there's both the sizes are large and the time complexity for evaluating the existing models. Essentially, lots of large matrix multiplications involved. And so the efforts to try to reduce this, the basic idea is instead of the full weight matrix, you keep a factor representation. There's both the reduced memory footprint and hopefully also reduced time for the performing the training and inference. So this is the basic low rank factorization we are looking at. And so in this work, essentially, we are just trying to compare two ways of trying to do the factorization of the weight matrices. This is the standard low rank factorization where the M by N matrix is factored into these two low rank factors, L and R. And so it reduces obviously the total number of parameters. And the alternate we are looking at is block low rank factorization, where take the same M by N weight matrix and we're just dividing it into blocks, and then each of the blocks gets a low rank factor, and then the unit that's so so here the number of parameters is where we have now B blocks along each of the axes, then the number of parameters would be B times M times R plus R times N. Okay, so now what parts to factorize? So this is a transformer, and while it's also some works have tried to also factorize the input embedding, that's the very first layer. That doesn't repeat for each of the layers. So we are focused more on, so the multi-head attention part essentially has 4 linear layers in it. And then the feed forward stage inner transformer has 2 linear layers. So essentially, this is where the majority of the parameters is. And so this is summarizing what the previous speaker has also mentioned in terms of how these large language models are used. First, there is a very expensive pre-training phase where there is this foundational model or the big model that is pre-created, for example, BERT. And then for various specific downstream tasks, that model gets fine-tuned. And so we are focusing on the fine-tuned part where we want to essentially use compression or factorization to be able to, because the fine-tuning involves both training and then after that using it for inference. So that's so this is essentially what this experiment is, to use these 2 different ways of trying to do the low rank approximation, that is the standard low rank and the blocked low rank. So first, one of the questions to ask is what's the characteristic of these actual matrices in the weight in BERT? Does it actually have low rank or not? And this is showing you do the actual factorization and then just look at by taking the top case singular values and then saying reconstruct and see what is the error. You can see that it's pretty full rank. There isn't any natural rank sparsity in these weights. So we can expect that this is not an easy problem. So, so this is the context in which this evaluation was done. This is the standard NLP benchmark suite called the GLUE benchmark suite. And we start with the pre-trained BERT model, which has 110 million parameters. And there are 7 tasks in the glue benchmark, including sentiment classification, textual entailment. And these are so essentially in these experiments, we're looking at 5 different levels of compression with respect to the number of model parameters. That is, the most compressed version gets it down from 110 million to 28 million. That will be a 74% reduction. And then the least compressed one is just bringing it to 77 million. So we want to evaluate it at these different compression ratios. And so I mentioned before, the downstream tasks, this will be evaluated on was in the glue benchmark. And for each of these, the whole experiment is done 6 times with random seeds after hyperparameter search. So one of the first things that we faced is that we didn't really expect is the factored models didn't, the base SVD factored model didn't always train. That is, so what does that mean? So essentially, we are taking the parameters at each of the stages in the transformer to the low rank factorization, start with that as the initial step, and then we want to pre-train. That is on the particular downstream task, and it just didn't train at all. And it depended, it would depend on the trial. Sometimes it would train, sometimes not, right? So, so this is showing what, so this actually happens even with the original unfactorized matrix for BERT matrix for sometimes, but the green shows the number of the fraction of times, essentially percentage of times in the trials that we basically just couldn't train with the low rank factorization. The orange shows for the blocked low rank. So actually the blocked low rank seemed to be more stable, and but neither of these was as stable as the base version. So one of the things that Ashim tried was to, instead of just starting with factorization of all the weights at the same time, do this in a staged fashion. That's essentially could go in either direction, first layer to the last or the last layer to the first. So what we do is just do the factorization for one stage, then do a few steps of pre-training, and then after that, do it for the second, and so on. And this is actually quite consistent across the benchmarks. With the standard non-blocked LR, the staged factorization really increased the stability. But for the blocked LR, it became less stable. So part of the reason to talk about this is maybe one of you give us a clue as to what's going on here. Or maybe you've seen something similar. But the good news is that with this staging, the LR factorization stability problems basically went away. It was as good as the unfactored version that's on the left. Right. Okay, so now one thing that Ashim found is that the extent of instability seems to depend upon the size of the training set. That is, when we have larger training sets, there is less problem with instability, and when we have very small training sets, it turns out that these glue benchmarks, they have the different data sets have different amounts of data. For example, the WNLI has the fewest; it only has 700 training samples. The ones that some of the others have more than 50,000. So this essentially shows the same kind of trend overall with respect to the downstream tasks that have large data sets and the ones that have small data sets. But the extent of the problem is magnified for the benchmarks that have smaller data sets. So, so these are essentially the results so far. So this is essentially an initial set of observations at this point and some challenges that we face. So the x-axis here is the represents the number of parameters. So we did these 5 levels of compression. So the one on the left has the smallest parameter, so that's the most compressed. And so that has the lowest score. So the higher is better with respect to the glue score. And the one on the rightmost is the least compressed version. And the dotted line shows what the accuracy, or it's an aggregate score based on the performance on all of the glue benchmarks. So what we can see is, so the green dots and the error bars, that basically represents the variation across the 6 different trials. You don't get the same results. So that is the staged low rank. So that is consistently the best. And then blocked. So we also did staging with I pointed out, right? It doesn't improve for the blocked LR. So here we are presenting the better results. So the form that's more stable also tends to have the better quality in terms of the it's kind of related, I guess. If it's not stable, then if it manages to converge, it's not doing it as good a job as the cases which are more stable. So essentially, we, stage low rank outperforms both non-staged low rank, which is the blue one, and block low rank, which in turn we don't have the plots here for, don't have data here for the staged block rank, which is not as stable. And so overall, for these benchmarks, for about half the parameters, that is, we want compressed by a factor of 2. In terms of the blue score, we are getting pretty much 95% of the overall score in this benchmark. So it seems like it's promising in terms of being able to actually perform well on these benchmark tasks. Okay, so to wrap up, so essentially, I guess first takeaway is we didn't realize how challenging it would be to create a factorized implementation for a full transformer network that actually trains on these downstream tasks. And so that's why I asked the previous speaker whether they'd done these, because we didn't really expect that this would be an issue that is, maybe you don't have that much accuracy, or you may not with different types of factorization, but just to get it to train was a challenge. So just repeat the base conclusion: staged LR factorization is effective. It's more stable and it outperforms standard non-staged LR factorization. And we tried this blockwise LR factorization, but that didn't work as well, especially it didn't benefit from, if you just don't do it with no staging, it's actually better than LR, but once you try to do the staging, one improves, the other one worsens. So what are next steps? Open questions. Clearly, this extending this to larger models to see, do these trends still hold? Can we see the same kind of benefits here as we have seen for the BERT model? Try to understand why is stage factorization improving quite consistently for all those downstream tasks when we use the base LR factorization, but not when we do the blockwise LR. And so another thing we're thinking about is maybe can we augment the low rank factorization with a sort of an error sparse matrix? So essentially something hybrid between standard unstructured sparse pruning, where amplitude-based pruning is done. So, but here maybe take the factors, look at the difference with the and then try to find on those spots where there is the largest magnitude of the difference between the factor approximation and the actual weight matrix. So that's so overall, this is very much work in progress. Seems quite challenging. Thank you. Definitely welcome insight from everybody in the audience.
I was wondering about these blocked versions of this. So how do you choose the block size? And is it related somehow to something that's going on in the model that you're trying to classify?
So I think here the block size is, block sizes. So the main thing that we kept constant was the total number of parameters. So if you choose fewer blocks, then you should have larger rank on total number of parameters in one block. As you increase the number of blocks, then these factors the rank is easier. If the base wants to be in the rank of 24, then the block one will have each one have a rank. But if you're trying to model and capture a smaller subset, that is more effective. If you don't do the staging, it actually is more effective. But once you do the staging in the learning process, it was the base was capture. Two factors trying to approximate the entire that.
I'm curious, what's the range of dimension in these matrices? It looked like in your singular value plot, it was like 800.
Okay, so the actual experiment, it was like, I think the base one
Of the
LR, the non-block one, for one of those set of constructions, I think it's 24.
but what are the matrix dimensions?
Well, the matrix, these are something like the bird is what that or
Okay.
I think the ML2 matrices are F by 4 at 6 times 4 times 6. So I think F, I believe number, there are 50 birds times 68, something like 1,000. Something will walk on the one. If you want to do it for larger one, but
Cool. Hi, everyone. Thanks for coming today. I'm Scott, and I'm in Fred Kilstad's group. Fred was scheduled to talk right now, but unfortunately he found out yesterday that he couldn't make it, so I'm talking instead. And I'm going to be talking about our work from PLDI this year. And so this presentation was originally designed for sort of the programming language community. So I'm going to try to skip through some of the slides quickly that are not needed so much for motivation and try to provide some extra contextualization if possible as I go along. So this work has a formal verification aspect. And by formal verification, I mean that we're not just trying to prove that our algorithms and our software is correct on paper, but we're also trying to provide mechanically checkable formal proofs inside a proof assistant. So sort of the big dream of this work is to try to grow a formally checked library of compiler techniques for mathematical computing inside Lean, which is a proof assistant that we're using. But the talk today is about our small seed contribution, which is a compiler for sparse tensor algebra. And this compiler is based on a really simple idea. And so in this talk, I'm going to try to explain that idea and its generality, basically. So I'll start with the input language. So on the one hand, we have tensor arithmetic notation. So you might think of this compiler as being maybe relatively low level compared to some of the other presentations. We're taking in the same sort of input that the Taco compiler would. But on the other hand, unlike Taco, we can also handle relational algebra queries and other types of queries. So on the right is sort of a simplified SQL query, and we can handle some problems like that by virtue of using this idea of positive algebra. So this was some prior work from 2007, which gave sort of like a relational perspective on a lot of different problems by sort of rendering them all as sum of products problems. So this notation has only a very small number of operators. It has element-wise addition, element-wise or Hadamard product, broadcasting, which is this arrow operator, and summation or contraction, which sums along an index. So this is our input language. And as I said, our goal is formal verification. So what that means is that we have to try to implement our compiler in a very simple pared down way so that we can actually reason about its correctness in its entirety. So as a sort of strawman example, I'll give a simple way of compiling this kernel on the left. So this is a product of 3 different vectors followed by a summation. So one strategy for compiling this into low-level code would be to generate a series of loops to compute it in a sort of bottom-up fashion. So we have one loop that computes the product of u and v and stores it in a temporary. We have another loop that multiplies that by w. And then finally, we have a separate loop to sum up the results. But this is very memory inefficient, of course, and performs a lot of redundant traversals. So of course, we'd prefer to have code that looks like this. This code is fused, meaning that the several products are occurring all inside one loop. And in fact, if you have a specific architecture in mind, you probably want to do a lot more optimization than this. But just for the sake of example, this is the sort of code that we want to generate. However, we want to deal with all sorts of different sparse data formats. So, in some talks earlier, the CSF format was mentioned. There's CSR and all these different formats that can be represented at hierarchically as a sort of composition of one-dimensional formats. So, for instance, you might have a data set which locally has various dense sequences of elements, but along the higher ranks is very sparse. So we'd like to be able to handle arbitrary data types such as these, but generating low-level code presents a sort of combinatorial explosion problem, and the resulting low-level code is very difficult to reason about. So formal verification, sparse tensor algebra is used in various sort of safety-critical or decision-making applications. Another application that might appeal to you is one where you'd like to be able to test your code on a simple, say your laptop, and then trust that a highly optimized version that generates code for a distributed system or maybe an accelerator is going to produce exactly the same result. So that's kind of one of the applications we have in mind. So our strategy for doing this is this notion of an index stream. And an index stream is basically a representation of a sparse computation. So an index stream can model a data structure. It could also model some implicitly defined data, but it can also model one of these composite computations like the three-way vector product from before. So what we've done is basically take these operators from positive algebra and define them as operators directly on index streams. So for instance, this product operation takes in 2 index streams and then produces an output index stream that computes their product one element at a time. And in this way, a complicated expression can be built sort of bottom up using these operators. So we've implemented a compiler that can compete with Taco and some relational algebra compilers, and verified sort of the core idea behind it. And the test implementation is only about 500 lines of code. So now I'm going to talk about 2 aspects of index streams. First, I'm going to give basically the definition. So an index stream is essentially a sort of automaton or a transition system, and I'm going to draw a few on these slides. So here I want you to just think of this as a state machine that has 3 states and 2 transitions between those states. And the first state is labeled Q. Now, I want you to think of it as a stream. So at each state, this automaton is allowed to potentially produce a value. So at these 3 states, it produces the values 2, 5, and 3. And these values are also indexed. So each state also produces the like index or sort of basis vector associated with the value. So a little more formally, an index stream is a state space sigma and an initial state. It has these 2 labeling functions that label each state with an index and value. And we make a couple assumptions about these indexing sets and value sets. So we typically assume the indexing set is totally ordered. And we assume that the value set is a semi-ring. So that means that it comes with a 0 value, which is important for having this notion of sparsity, and addition and multiplication operators. As well, index stream has a ready function. So the ready function is Boolean valued, and it labels each state with its readiness, which essentially allows the state machine to take as many internal transitions as it wants to that do not produce any observable values. And then finally, importantly, there's a skip function. So I simplified the diagram a little bit so far. In fact, there's not a linear sequence of transitions between these states necessarily. So in fact, the transition function is labeled by a desired index value. And this is used to model data structures that allow efficient access to particular values. So we'd like to be able to make use of, say, binary trees, which provide a way of efficiently jumping ahead to a particular index. And that's the motivation behind this abstract definition. And for the precise details of all these type signatures, please see our paper. And finally, there's a way of evaluating an index stream to a mathematical object. So in this case, we see that the stream produces values 2, 5, and 3 at indices 1, 4, and 5. And so we get a vector something like this at the bottom. But these streams are not limited to one-dimensional problems. And we tackle higher dimensional or higher rank tensors in a very naive way. We simply allow a stream to produce other streams as values. So in this example, there's an outer stream that goes down along the rows of a matrix. And at each one of these states, it produces another stream that produces the values for that row. So the evaluation of this stream on the left might look like the matrix on the right. And I should note that at each level, you might choose to use different data formats. So there's a lot of user customizability of the system. And then the other key thing we do is define the stream multiplication process, which is very simple. So recall merge sort. The merge operation in merge sort takes 2 sorted lists of values and produces a single merge list as output. So you can think of this as a state machine by initializing a couple of pointers at the front of the lists, and then at each step, output the smaller value and advance the corresponding pointer. So we take a series of transitions and we end up with a sorted output list. Now, on the other hand, if you want to intersect 2 lists, you do essentially the same thing, except that you only output in the states where both of the values match. So I've denoted some other states in here that you can say are not ready to produce any output. And likewise, since the arrays are sorted, you might want to skip ahead, maybe use a binary search or a galloping technique when one of the values is very far behind the other. So in fact, this idea translates very, very straightforwardly to multiplying vectors element-wise. The only difference is that we output the product of 2 elements alongside the index as we go along. And so I just want to call attention now to the fact that these stream state machines can represent not only input data structures like U, V, and W in this example, but also the sort of dynamic process that computes U times V over time. And in fact, the code generation process is very straightforward. It fits on one slide. The compiler in its current state produces a loop nest for any given hierarchical problem by sort of recursing along the structure of the streams involved. So So I guess the observation here is that we've found in our test so far that this combination of efficient compressed data structures for tensors, plus this simple sort of merge product operation is enough to match some of the performance from Taco. And also it's enough to match some performance by compiling relational algebra queries from like industry standard data sets compared to DuckDB, which is, and SQLite, which are, DuckDB is an analytical database. And it's all rather simple. So I'll just quickly run through, we did some benchmarks and we can produce essentially logically identical code to Taco. So on some standard tensor benchmarks, we get a 1x speedup. And on some other benchmarks, we are a bit slower, but there's no conceptual obstacle to sort of implementing Taco's optimization for tensor addition as a stream. And then on some relational algebra queries, we get quite a large speedup over SQLite, which is an interpreted system, and DuckDB, which is a more highly engineered column-oriented database. And I'll also note that if you've seen the worst case optimal join algorithms, we happen to output code that matches their performance. So there are some tasks where you get asymptotically better performance than standard database engines. And finally, I said at the beginning that this is about formal verification. Well, the core of the proof is very simple. The core of the proof is essentially that this stream evaluation function we have is a homomorphism with respect to products and sums. So what we want to show is that if we have two streams which satisfy certain lawfulness criteria, which are technical criteria that make sure that they make progress and traverse indices in order, then it's true that evaluating the stream product of A and B is the same as evaluating A and evaluating B and then multiplying those vectors. Similarly for sum. And this part we have recognized. So in conclusion, I'll just talk a little bit about some like current work and maybe future work. So one core piece is extending this formalization of the model to an end-to-end verification of the compiler. So this entails ensuring that the syntactic representations of streams that we use for compilation match up with their mathematical model, and then connecting that with the proof that that model is correct. And it involves some low-level reasoning about imperative code. We're also looking towards producing not just CPU code, but also accelerator code. It turns out that streams are a pretty reasonable model for certain types of data flow hardware. So we're looking toward modeling that data flow hardware as a set of data flow hardware blocks as like stream combinators as well, so that we can verify that separate backend target. And we're exploring higher level optimizations on streams that are necessary for performance. So that's about it. I can take questions.
Yeah, very nice talk. Yeah, so you mentioned the similarity of this sort of to general data flow model of computation. Yeah, the stuff that I mentioned at the end with parametrized data flow, you essentially can view, there are very strong similarities with this. Essentially, a data flow graph represents the computation. But related to that is our development was motivated by sort of data dependent. So right now, I didn't see any sort of data dependence in your algebraic operations that you had, but oftentimes we want to be able to screen out the data from streams or have conditional. So essentially you produce, the data ends up going into one stream or the other. Do you envision extending to things like that?
I think, I'm not completely sure I understand, but I think to some extent we do this. So I didn't go into much detail into like how the relational side looks, but it turns out that this this like merge operation, which the way it works is that it looks at sort of the current index of all the streams involved and feeds that back to all of them. So there is some sort of like forward-backward communication, like across different streams that are being merged. There is a possibility of maybe like instantiating two pipelines, passing some Boolean check to both of them, and then using that to like filter out entire chunks of data or not. Well, thank you.
Right. My talk is really an advertisement for the poster session. So my student Abraham is going to be presenting there. Thank you to the organizers for inviting me. This joint work with Abraham, Rachel, and my former postdoc advisor, Misha Kilmer. I'm going to talk about kernel approximations. So we've seen kernels different times. What I mean by kernels may be slightly different in some of the talks. So this is the core of the problem. This is, you're given a set of points in 3 or 4 dimensional space. The source points and their target points. And you want to compute the pairwise interactions between them. So you're computing a matrix. And the size of the matrix can be large. It can be in the order of hundreds of thousands. And it's dense, and you don't want to compute it if at all possible. Okay, so even forming this matrix is expensive, but what you want is a compressed representation. And if you were to naively apply the SVD, it would be cubic. So I don't have to tell this audience. So what we want is linear time algorithms. So this is a fundamental problem that appears in many areas of scientific computing and machine learning. Perhaps the earliest version is n-body computation. So there was a tree code in '86 that, and it's used in molecular dynamics and astrophysics to compute galactic interactions. In PDEs, it's used in volume and boundary integral formulations. In what was the top 10 algorithm of the 20th century, the pass multiple method, it's used for off-diagonal interactions as well. And in machine learning, it's used for Gaussian processes or more generally any kernel method. Okay, so that's the core of my problem. So I have a slightly different problem that I would like to address as well. I don't want to just compute this matrix one time. The kernel is a function, and it may be parameterized through a set of hyperparameters. And I may want to compute this kernel computation for many instances of this hyperparameter. For example, you're training a GP model, and you want to train it over the hyperparameters. And so you want to do this over and over again. So how does this is both an example of a kernel and a parameter. So the parameters here are correlation lengths that scale the relative distance between these 2 points. Okay. So the core of our idea is to compute a low-rank representation like this. So this is a kernel that's parameterized by theta. And we have 2 low-rank the factors U and V transpose that are independent of the parameters. And then there's a middle smaller matrix that does depend on the parameter, and that's easier to evaluate when for a given value of theta. Okay. If you're scratching your head, where is a tensor? I'll get to that in a second. Okay. So that's an offline online type of approach. We view this as a tensor decomposition problem through function approximations. I'll talk a little bit more about it. The important point of our algorithm, it's linear in the source and target points. So from cubic, it's down to linear. So we do this in 2 ways. So we do it using the Tucker method, which we have seen several talks about. And we have Tucker compression methods, which are perhaps of independent interest to not just kernel problems, but Tucker computations in general. And then we'll look at tensor train-based approaches. And here we use more or less standard tensor train tools. We use them in somewhat innovative ways. And then I'll show you extension to parametric kernels. And if you're interested, this has appeared, the Tucker part of this work has appeared in this paper last year, and we're trying to put out tensor train work. So that brings out the outline of my talk. I'll first talk about the Tucker-based approach, and then very briefly talk about tensor train and really go to Abraham's post. You'll hear me say that much. Okay, so I have to convince you that it's a tensor problem. perhaps it's perhaps wrong to look at a matrix problem because it's fundamentally a tensor problem. Okay, so why is that? So suppose I want to compute the pairwise interactions between the set of points x and y. What I do is I use Chebyshev approximation to interpolate these set of points to a set of Chebyshev points. That's represented by this blue factor matrix F sub S. And similarly, the target points Y, I also interpolated to the Chebyshev points and using this factor matrix F sub T. And the middle matrix M computes the pairwise distances between these Chebyshev, and that's far fewer than the number of original set of points. That's why it's a low rank representation. But fundamentally, you can look at this as a matrix problem of n squared by n squared Chebyshev nodes, or you can look at it as a 4-dimensional tensor, n by n by n by n. So in 1 dimension, you're going to have a matrix. In 2 dimensions, you're going to have a 4-dimensional tensor, and so on, right? It's 6 dimensions. Okay, so the core of our idea is first use the Chebyshev approximation, which I call black box fast multiple method. That's one set of approximations. Second, the core matrix, we look at it as a tensor, and then we compress it. Okay, so that gives us this M hat. And then you have to massage the factor matrices somehow. The details of that I'll skip. It's not that difficult. In the Tucker case, you're going to end up with some factor matrices. The matrices F sub T and F sub S have some structure, even though I've written it as a dense matrix, they have some structure. So you can exploit that structure to do it efficiently. In a tensor train, you have to do slightly different things, but fundamentally, those are the 2 steps of our algorithm. Parametric case is very similar. The only difference is that the middle core matrices are the ones that are parametric. Okay, now I'll talk a little bit about how I compute these tensor approximations when we're using Tucker. So to do that, first we have to understand how to do it for a matrix. And I'm going to use randomized row interpolated decomposition. So I recommend this review paper by Halcomer and Dimitro. So if you want to compute the low rank approximation of a matrix, the steps involved are you estimate the range of X, and then you identify a set of indices, the rows of X, and then you patch those 2 things together to come up with a low rank approximation. The advantage of this is that it avoids computing, it's efficient in the way you access the matrix. The second step, you don't have to access the matrix in its entirety, only a subset of the matrix. And that really has an impact when it comes to tensors. So some details about the steps are, in the first step, you draw a random matrix, you compute a sketch of the matrix. So I compute a sketch this way. Think of the random matrix as a Gaussian random matrix. Like all good numerical linear algebra, after you sketch, you do a QR factorization, so you have an orthonormal basis. So you could compute a low rank approximation just with that, but we turn it on its head. So we transpose the Q, we do a pivoted QR to identify well-conditioned columns of Q transpose and similarly rows of Q. And together with that, we get this factor matrix. Okay, so once we understand how to do this for matrices, it's easy to do it for tensors. You unfold it with n-dimensional tensor, you unfold each mode independently, apply this randomized row interpolated decomposition to get that factor matrix, and then you take the indices from the unfolding. Then you can compute the core, and here's where the tensor approach is efficient. So when you have to compute the core in a HOSVD style, you have to compute the orthogonal matrices times the full matrix, full tensor. So you don't have to do that in this case. You just have to go to your tensor and extract the appropriate entries. So that's one reason why it's very good. So that's the final approximation you get. But the other reason it's really good is it preserves the structure of the tensor. So what do I mean by that? So imagine the tensor had sparse or non-negative entries, and you wanted your decomposition to preserve that. There's several ways of doing it. So ours does it in a special way that the core exactly reproduces entries from the original tensor. So if your matrix, if your tensor M is sparse, G is sparse. Furthermore, there's another important property, which is that not only that the core has exact entries from the original tensor, the approximation exactly reproduces a certain number of entries exactly. So that's an interpolatory property of this tensor. It could be useful in applications. It's not super critical for here, but it could be useful in other applications. We used 2 other variants in this paper. One that's subsample. So you don't want to form the full tensor. So we're doing the sketching process. You subsample it, compute the sketch, compute the row interpolated decomposition. That's one variation. So it requires fewer kernel evaluations. Second is the Kronecker RRID. So one deficiency of the randomized approach is that you have to generate a lot of random entries. So you can avoid that by generating structured random matrices. So we use Kronecker, but combine it with the interpolated decomposition. Finally, we have if you prefer the sequentially truncated version, we've done that as well in an earlier paper that appeared in SciMods a couple of years. And there we have actually shown it to work well on large sparse tensors. Okay, so how does this work in practice? This is the setup of my problem. I have to compute these pairwise interactions between the sources and targets that are a certain distance apart and certain angle. Here are three kernels. They have importance in different areas. This is from interpolation. This is from Gaussian processes, and this one's from PDEs. So different areas. And our three methods, the bottom line is the three methods are comparable in error to matrix-based approaches. But in terms of runtime, the speedups you get from between 5 and 15. These kernels are not parametric yet, and I'm going to talk about that very soon. So for parametric kernels, I'm going to talk about two cases, exponential and return. And both of them are parameterized in such a way that there are two hyperparameters. So what was a 4-dimensional tensor because of 2D interactions is now 6-dimensional because of the 2 extra parameters. The second one is the Matern kernel. It's a complicated expression. I don't want you to know, but I just want to point out that it has 2 extra hyperparameters that are different in meaning than the first one. Okay, so for this problem, just a matrix-based approach, there's no offline time because for every new evaluation of the hyperparameter, I'm going to compute it. It's about 10 seconds. Whereas for our approach, we get relatively good accuracy with much smaller online time. So in the second case, this is almost a 10x speed up. And while you'll say that you can say that the absolute amount of time, it's like 30 seconds, not that long. But what you should understand is you have to do hundreds of thousands of these computations. So this can really make a huge impact. Finally, if you can also compute a low rank approximation of the form where the sources and targets are the same. This is a little bit harder problem, but you have to assume that the kernel is sufficiently smooth that allows you can do it. So it's called a global low rank approximation. But another issue here is that we want it because the source and target points are the same. You want symmetry. So you want a symmetric tensor decomposition. In the Tucker case, it's easy. You just have to copy your first n core matrices to the last, and you can show that preserves the symmetry. That has applications in Gaussian processes. Actually, not just symmetric, it also preserves positive semi-definiteness. That might be important. So this is a precipitation data set. It's not a very high dimensional machine learning data set, but nonetheless, it's 3 spatial dimensions, so it's 6 tensor dimensions. And even with very low tensor ranks, we get very good accuracy because the kernel is very, very smooth. The total number of points here are 600,000. So I couldn't form the matrix. So finally, this is the important stuff. So even when we were working in the first project, while we got impressive speedups with Tucker, we knew that that was the wrong approach moving to higher dimensions. Tucker suffers because the core storage of the core tensor is very challenging. So we knew at the back of the mind that tensor train was the right way to look. There are some issues with tensor train. It's not so easy. The mechanics of it is fairly easy, but to actually get it to work for this particular application is challenging. So what we had to do was, if we had to compute cores with this particular ordering, the spatial points are arranged first, then the parameters are arranged and the target points are arranged in that order. It turns out not to be the best way to compress the tensor. The tensor train compression depends a lot on what order you process it. And we have to process it in a specific order because ultimately we care about a matrix low rank approximation. So we have to preserve that order in some special way. So what we found, or actually Abraham found, was that it turns out if we reorder the variables, that's the right way to look at it. But you've gotten the wrong tensor train decomposition. You need to permute the tensors back. That's in Tucker, it's fairly easy to do. Tensor train is not so easy to do. So we had to figure out how to do that. And there are lots of details, and I encourage you to talk to Abraham for all of them. Cut to the chase, tensor train is better than Tucker. So with that, so we have this, I think, fairly new way of looking at kernel low rank approximations through the lens of tensors, and perhaps more matrix problems can be looked as tensors. This is one of them. Our cost is linear. The details are in the types of tensor trainer, types of tensor decompositions we use. We developed these randomized algorithms for Tucker, which I believe have importance in many other, could be used for many other problems, not just kernel low rank approximation. So with that, I'm happy. I don't want to keep you from the posters. Thank you very much. Yeah, in the words of Krista. Yes, please. With FMM? Yeah, I haven't really compared because the question is which version of FMM are you using? Like there are many algebraic, semi-algebraic, analytical. So I'm using one particular benchmark. It is competitive with many of the matrix algorithms, but it's hard to evaluate with all of them. I don't know if that makes sense. And the other point is that FMM tends to be very kernel specific. The kernel independent, yeah, this is what I'm using is a kernel independent algorithm. That's right, yeah. So I have to know exactly which one you're talking about. But I don't know that particular one, but but what I mean is I haven't compared with that particular one.
Connection with the butterfly factorization is, I also see in the poster there's a butterfly factorization.
Yeah, that's a great question. So I didn't say this, but I'm assuming that the kernels are smooth. So butterfly factorizations, as I understand it, are meant for kernels that are oscillatory. So from wave type problems. So we're assuming a certain smoothness in the kernels, which not in this problem. I don't know how to do for those problems, but it would be interesting. Thank you.
Particular announcements, the poster session will go to 5:45. So maybe that's the one thing. Yes. Yeah, please come between 8 and 8:30 and we'll have somebody at the door.